Hello and welcome to the MOOC on optical communications. In this module, we will talk about numerically solving nonlinear Schrodinger equation by a method called as split-step Fourier method. Okay. The basis of this is two observations. One, we considered a situation when gamma was equal to 0, that is there was no nonlinearity in the fiber. So, you have your envelope propagating and it is subjected to only dispersion. And how did we solve that resulting set of equation? We actually understood dispersion, that is propagation of the pulses through the fiber with only dispersion acting on it, by going to the frequency domain. That is, we took the Fourier transform, right, and then to the Fourier transform of the envelope function we multiplied it by a phase factor, and after multiplying it by a phase factor we came back to the time domain by taking the inverse Fourier transform. Now assume beta 2 is equal to 0, go to gamma, that is when there is only nonlinearity. How did we solve the resulting set of equation, the nonlinear equation? What we did there was that we formally integrated in the time domain, right. It also resulted in a complex phase factor, it was e to the power minus j gamma a square into z, right. So, we actually had to take the integration with respect to time and we did that. So, to account for nonlinear effect, right, we had to work in the time domain. To account for dispersion we had to work in the frequency domain. So, this interplay of frequency and time is what is captured by this so called split step Fourier method, and the idea is very simple. You start with a fiber, okay, of some length which you want to propagate. So, let us say at z equal to 0 is the fiber input, at z equal to L is the fiber output. You need to know, what are the things that you need to know? You need to know A at z equal to 0 as a function of time. This is something that you would know, right, because you are the one who is actually sending the pulse into the fiber, right. So, you would know what would be the initial pulse envelope at z equal to 0. You should of course also know the material properties of the fiber. You should know what is beta 2, which is usually a quantity measured in picosecond square per kilometer. You should also know the nonlinear coefficient gamma. In case you want to include loss, which is measured in dB per kilometer, you should include loss also into the equation. However, we will, as we said, we are not considering losses here. What you now do is, you imagine the fiber is being split into steps of delta z each. Okay. Now, what we do here is, we first account. So, this is called the asymmetrical split step method, but this is the simplest one to explain to me. So, I will not go into the variations of the numerical methods. So, there are symmetric split step methods, then there are various other ways of solving this NLSC. This asymmetric one is the simplest one to understand. So, what you do is first account for dispersion in the frequency domain or work in the frequency domain and account for dispersion. Then account for nonlinearities, right, account for the nonlinear effects by working in the time domain over one delta z step. Repeat this steps, okay, until you reach the fiber end. We are assuming that the pulse envelope is propagating along the plus z direction. In case you want to look at propagation along the minus z direction, you have to change the terms, the signs of the term in the Schrodinger equation. Instead of taking del A by del z, you have to take minus del A by del z and everything will be the same. Okay. So, I am not going to look at how the wave is propagating backwards, I am going to look at how the wave is propagating forwards, and this is the step that I am going to do. Of course, this is just a equation that I have written, I mean just a statement I have written. First account for dispersion in the frequency domain. How am I going to account for that in the frequency domain? Remember what happens if you zoom up onto one step delta z, what you see here is that you actually have a frequency transformation followed by, there is a NL which is a nonlinear step, correct. D is the dispersion step. So, this is called as a dispersion step because you are accounting for dispersion in the frequency domain. Now, to account for dispersion in the frequency domain, you actually have to put an interface here. These blue lines tell you that anything that happens inside the blue line is in the frequency domain. Anything that happens outside the blue line is in the time domain. Okay. So, you come in with the time domain, okay, and then you convert from time domain to the frequency domain. Now, what will give me the time domain to frequency domain conversion? So, this is my frequency domain picture. So, how do I convert that into the frequency domain? Well, I have to take the Fourier transform. Now, on a computer I can't really take the Fourier transform in the form of say some e power minus j omega t g of t dt for a given time domain function g of t, correct. On a computer I can't really do this integration. I have to use a numerical Fourier transform, and what is the numerical Fourier transform? I have to use fast Fourier transform, right. I have to use DFT, but DFT is nothing but FFT. So, I have to use fast Fourier transform. So, what I have to do is I have to fast Fourier transform the input signal. Again, the basic question is, do I have the input in the continuous form or in the discrete form? I have input envelope function also in the discrete form, because no matter a of zt, whatever the shape that is there, you can't capture that shape on the frequency, I mean on the computer. What you have to do is to sample that function, right. You assume sufficient number of samples so that they are not really you are not missing out information. So, you take into account sampling rate or whatever. So, you have a sufficient number of samples which will represent the original continuous time signal. So, the first step in fact to be putting on the computer, you can think of it as even the 0th step, is something that you start at a equal to 0, right, and you sample this. So, I write this as a of 0 t n just to indicate that this is a sampled signal. So, you start with a continuous time signal a of 0 t and then you sample this so that it can be represented on the computer. So, this is kind of an array for you. So, you can represent this one on a array. So, if you were to program using MATLAB, you would be putting this as an array and that would be stored as a n dimensional array. So, the number of sample points will determine the size of the array. Once you have that array, you have to remember mentally that this is still at the input fiber input end. What you have to now do is to take the first step in terms of the fast Fourier transform. So, what I am doing actually here is FFT of a of 0 t n. Please note that t n is my notation to indicate that this is a discrete time signal. Okay. So, you have to take the Fourier transform to the discrete time signal. Now, you are ready. What is formally this is equal to, or what is this analogous to? This is equivalent of a of 0 comma omega, right. So, you have taken the Fourier transform to get into the frequency domain, which is exactly the step that you did back when we discussed dispersion inclusion, right. We did this in the 4 step procedure. First step is to start with a of 0 t and then take the Fourier transform. Third step is to propagate and then back to the time domain, right. So, this is my first step in that sense, right. So, start from a of 0 t, take the Fourier transform. Now, you have to propagate this into the Fourier into the distance delta z. How am I going to propagate this over the distance delta z? I have to multiply, right. So, remember a of 0 omega got multiplied by e power minus j beta 2 delta z divided by beta 2 by 2 into z is the omega square. So, e power minus j omega square beta 2 z by 2 was the phase factor that got multiplied to this a of 0 omega, right. So, to the Fourier transform you multiply by this phase factor, but you are now sectioning the fiber, you are cutting the fiber into sections of delta z and you are propagating over only one small portion delta z. In that portion you are accounting for the dispersion. Start with the discrete time signal, take the Fourier transform, propagate it, which means that you multiply each frequency component by this particular phase factor. Now, you have completed the third step. What would be the fourth step? Go to the time domain. So, how am I going to go to the fourth time domain? I have to take the inverse Fourier transform, or in this case it is going to be inverse fast Fourier transform, right. So, that is as simple as that. So, after we have done the FFT operation, I have to multiply this FFT version with the phase factor e to the power minus j. Again the frequency omega will not be continuous, it is going to be discrete, right. So, it would be e power minus j omega n square, beta 2 you should know what is delta z is something in your hand divided by 2. So, this is what you are going to multiply to this. Then what you do is you go back to the time domain by taking the Fourier inverse Fourier transform. Okay. So, if you do this, so this would be the propagation step, and after that you have now come back to the time domain. So, after you have done this one, this is what the signal that you are going to get. This would be A of delta z T n, which is now purely dispersive step. Okay. It has been purely dispersive step, and what you have obtained as a result of this is to account for the dispersion. I hope this is all understood. Now, one thing that you might get a little bit of a problem is that where what should be the value of omega n square. If you know that you have sampled signals at a sampling rate of fs, if the initial time domain signal was sampled at a rate of fs, then the frequency components will be n, fs by n, where n is the total size of the discrete array that you have considered. So, n fs by n will be the mth frequency component. This is the mth component frequency, but this is the offset frequency. So, you have to add to this the original signal frequency or the central frequency omega s as well. So, this is what you have to take the magnitude square. So, you actually have omega n square given by the offset value omega s plus n fs by n into whole square. So, this is how you generate the frequencies, and this is what goes into this exponential term or the phase factor term. Okay. So, I hope the dispersion step is all understood. There is not much happening out there. Start with the time domain, go to the frequency domain, propagate it through the dispersion step and get back to the time domain. Now, how am I going to include the nonlinear step? Well, nonlinear step, if you go back to what we discussed in terms of the nonlinear Schrodinger equation, you had to multiply that one by a factor e to the power minus j magnitude of 0 to t magnitude square times z, or rather gamma times this one, right. Again, I am not propagating over the entire z, so I will be propagating it over only delta z, and it is not a of 0 t, but rather whatever the result of a of delta z comma t n. Okay. So, whatever the result of this operation which we denoted by a of delta z t n, that must go into the expression over here. So, you need to consider that one, and this is the propagation term that you are using. So, this would be a of delta z comma t n. Okay. So, this term goes and gets multiplied with delta z and e to the power minus j gamma. So, where this term that we have used in the phase factor, the green one, is simply the result of the dispersion propagated step. Okay. So, after you have done this one, you multiply this result what you are getting by e power minus j gamma magnitude of a t n delta z. I do not have time, so I am not writing that one, multiplied by delta z. This is what you get. Now, what you do is you repeat this entire process through the next delta z step. Okay. So, let us put all the results together here. So, what you need to do is you start with a of 0 t n, which would be in your time domain, then take the FFT, then propagate this one by multiplying it by e power minus j omega n square beta 2 delta z divided by 2, and then take the inverse Fourier transform of this. After you take the inverse Fourier transform of this you have to multiply by e to the power minus j gamma a of t n magnitude square into delta z. Okay. And then you repeat this process n times or maybe m times, such that m into delta z is equal to L. So, if you have taken the fiber and sectioned it into m sections, then you have to repeat this process for every m section. So, this is the output of the first section. Do the same thing again. You have to start by going to the Fourier transform. So, if you were to go to this one, whatever that you have called here, you will have to repeat the process. So, you have to take the Fourier transform, then multiply this one by e power minus j omega n square beta 2 delta z by 2, again take the inverse Fourier transform and then multiply the whole thing by e to the power minus j, but this time you have to use the result of this fellow in the bracket. Okay. So, you continue to do this and you will be able to get the pulse propagation, and there is a simple program which I will give you. You can experiment with that one, okay, for whatever the values of beta 2 and gamma that I will give you. You can experiment with it, see how self phase modulation can be realized and how one can modify the code to include cross phase modulation. All these things I will leave it to you. Okay. Now, before finishing off this nonlinear terms, let us very quickly talk about two additional nonlinear effects. One of them is very important, the other one is actually a nuisance, at least for communication systems is concerned, but for sensing applications that is very important. So, you have inelastic scattering process, which is the result of phonons and photons talking to each other and exchanging energies via the lattice vibrations. So, whenever an optical signal propagates, it interacts with the material, and because this material will have certain acoustic vibrations, you are going to get phonons generated and there would be energy transfer. So, this is some process where energy is actually getting transferred to the lattice or transferred to the material of the fiber, not really getting it back. So, this is a lossy process, it is not lossless process. In the case of four-way mixing, energy from pump 1, pump 2 and the signal will go to the fourth optical wave, which means you are actually able to extract that energy. You can think of that as elastic scattering. This one is inelastic scattering. So, it is a lossy process. What are the two types of nonlinearities that we have to look at in the inelastic scattering process? One is called as the Brillouin scattering, and this Brillouin scattering is a particularly troublesome process because it has the lowest threshold for nonlinearity. So, this is the lowest nonlinear threshold, which means of all the nonlinear effects that we studied and the one that we are going to study, the SRS, this one is the one which occurs first. Okay. And what will happen when this occurs is that you start with a pump or you start with one of the signals, okay, at say omega s, and after propagating through the fiber, while this wave is propagating along the positive z direction, there will be a backward travelling Brillouin generated signal. Okay. So, this backward travelling Brillouin generated is called as the stimulated Brillouin scattering. You can also have a non-stimulated version. So, you can have a spontaneous Brillouin scattering, but that is very small process, like very negligible process, we are not going to look at that. But whenever you have an optical wave propagating along the z direction, there will be a backward propagating Brillouin scattered signal, and this is called as stimulated Brillouin scattering, and it is usually downshifted in the frequency, correct. And then the amount of downshifting depends on the material, but for most single mode optical fibers this is around 11 gigahertz. Sometimes this can be tuned anywhere from 10 to 12 gigahertz, but it is quite normally occurring at 11 gigahertz. So, in case you have one more channel at 11 gigahertz, you are in trouble, or you are looking at let us say 25 gigahertz bandwidth, right. So, your pulse spectrum, if you are using a QPSK or something else and pulse shaped, the pulse is occupying about 25 gigahertz, right, because you are sending information at say 100 gigabaud or 50 gigabaud, the pulse spectrum is occupied in the entire 25 gigahertz, and now you have a Brillouin scattering signal going back, which means there is going to be a crosstalk at 11 gigahertz. So, the pulse which is coming back is going to talk to the components at 11 gigahertz away from the carrier frequency and then give rise to crosstalk problem. So, this SBS crosstalk in communication systems is particularly bad, and it is bad because the threshold for most step index fibers is just 1 milliwatt. So, if you go beyond 1 milliwatt, you are already generating SBS. There have been lot of efforts in reducing this SBS, and there is in market what is called as a increased SBS threshold fiber. Okay. So, these fibers were originally fabricated by or developed by OFS, and these SBS threshold fibers actually have a higher threshold compared to the original fiber. So, instead of 1 milliwatt they would have a threshold of say 2 milliwatt or 5 milliwatts depending on the design of the fiber, and this is a very important effect. Another way you can avoid this SBS thresholding effect or the SBS effect is to modulate your pumps or modulate all the signals at a rate which is quite high, so that the effect of Brillouin scattering is removed. However, for cases where you have continuous wave signals, Brillouin unfortunately will be the problem. It is actually going to limit the amount of power that you can put into the fiber, because the moment you cross a threshold, well, you have Brillouin scattering up there. Where is this Brillouin scattering useful? In addition to this SBS effect, in addition to the downshifted version, there will also be an upshifted version. Okay. The upshifted version is very small in amplitude compared to the downshifted version, but this one is temperature dependent. Okay. This temperature dependent process means that, which again occurs at around 11 gigahertz or maybe slightly less than that, I am not very sure, but whatever it is actually temperature dependent, and you can actually use this to probe the temperature of a system. So, you can send in the you have a fiber there, you can make temperature sensors by taking the fiber and winding it up say on the boiler room, and as the signal propagates, right, and it experiences the Brillouin scattering depending on the temperature, it can be used for sensing the temperature when the fiber is in contact with the boiler, right. Of course, you have to take care that the fiber does not melt, but if you take all those cares, then it can actually be used as a nice temperature sensor. In fact, that is one of the major uses of that. One can also use this SBS effect for implementing what is called as optical phase conjugation, right. The efficiency is not very high, but optical phase conjugation is one method to avoid or mitigate all the nonlinear effects in the fiber. So, all the harmful nonlinear effects can be mitigated by applying optical phase conjugation, and one way of generating optical phase conjugation is to use stimulated Brillouin scattering. Okay. So, this is about Brillouin scattering. Now, what we will look at is what is called as Raman scattering. The name Raman must be very familiar to you. He was the scientist from India who got a Nobel Prize, the first Nobel Prize for science work in India, and what he observed is very simple. He observed this effect in the crystals. Now, it is observed in almost every other material. You send in light, what happens is you will also get two lights which are called as Stokes and anti-Stokes. Okay. Stokes will be downshifted in frequency, I suppose, and then anti-Stokes will be the one that is upshifted in the frequency. In terms of the wavelength, you send in the pump and then you get a signal at longer wavelength. Usually the Stokes is quite stronger compared to the anti-Stokes wave. So, you send in at say 1550 nanometer, you will get one component at 1560 nanometer. I am just giving the numbers, these are not exactly the numbers that I am looking at. So, you send in a short wavelength, the power of the short wavelength reduces, but a new frequency, a new wavelength component comes up at a longer wavelength, and this is what is called as a stimulated Raman effect. There is also spontaneous Raman effect, but spontaneous Raman effect is very weak, and therefore, we do not consider, just as we did not consider the spontaneous Brillouin scattering. The stimulated Raman effect is both useful and harmful. Okay. It is useful because one can actually put up a Raman amplifier, you can actually make a Raman amplifier for communication systems which will work beyond the 1600 wavelength. Remember, the erbium doped fiber amplifiers which we discussed cannot really work for say 1600 nanometers, because the gain spectrum is usually from 1525 to 1560 or about 1570 nanometers. Beyond that, there is a short wavelength band which is important because the attenuation is less, but I can't use amplifier, erbium doped amplifier there. So, what people have done, this is about 10-15 years ago, what they did was they put up a Raman pump, and the Raman effect is very interesting because it is kind of a distributed amplification. It is not at a particular location. The Raman effect actually, if you send in the pump from the backward direction, the signal which is coming over here, it will start to increase because this pump continuously loses power and transfers the power to the forward propagating signal. Okay. You have to tune the wavelengths or frequencies appropriately such that this is at a shorter wavelength, this is at a longer wavelength. So, if you do that, you are able to send in, you are able to amplify the signal beyond the 1570 nanometer range, and you will be able to combine EDFA and Raman amplifier and Raman amplification, and you can actually have a long wavelength band of communications. The L band communications which happens at 1600 nanometers actually uses this stimulated Raman effect or stimulated Raman scattering. The gain spectrum of the stimulated Raman scattering is very wide, which means that it actually has a peak, or rather a double peak at about 13 terahertz frequency shift. So, if you start with a frequency of say 10 terahertz, then at around 23 terahertz you are going to get a peak shift, that is the conversion from the pump here. So, if you put a pump at this wavelength, then the pump here would be very nicely coupled. So, the coupling between these two is very large at this particular, it is about 13 terahertz or 11 terahertz, does not really matter. I can give you the exact number later on. Okay. Why is stimulated Raman effect bad for communication systems? Well, for communication systems, especially in the WDM situation, you have multiple channels propagating, right. Even in the range of 1525 to 1560 nanometers, which is the C band, there are about 200 channels propagating. So, on a given optical network, right, you will have all these channels more or less populated along with that. And if these amplitudes are changing, maybe especially when you are using all the channels are on off key modulation, then the worst case scenario will be the one at the lowest wavelength fellow, right, because it gives power up to the next wavelength, gives power to the next wavelength, next wavelength, next wavelength. So, the lowest wavelength actually gets attenuated very rapidly, the longer wavelength fellow actually gains a lot of power, but you do not want that extra power, because if you now go into an erbium doped fiber, the erbium doped fiber is not going to amplify all the wavelengths in a uniform manner, because there is a gain spectrum to the erbium doped fiber. Granted, you can put some equalizer, but it is not going to put the same kind of amplification for all of them. What happens is the one which has a higher power will usually saturate the amplifier. Okay. It is called a spectral hole burning. It basically saturates the amplifier, and all the remaining ones do not get enough amplification. It is like 10 people go in, the most hungriest one gets to eat all of the food, and then the remaining people who might not be completely hungry will get little power, or the one who is very strongest eats all of the food, and the one who is weak but hungry does not really get any power. So, what happens is that the amplification will not be uniform, not all the optical signal to noise ratios will not be the same for all the channels, and you have to then deal with the fact that the performance will be non-uniform across the channels. The second thing is that when the power transfers, it is not just the power that is getting transferred from a shorter wavelength to the longer wavelength, it is also information getting transferred. Okay. There is a crosstalk happening from shorter wavelength to the longer wavelength band, and this crosstalk will destroy the information, or at least it will interfere with this one. This is a very important effect, because Raman scattering, the gain spectrum of the Raman scattering is very wide. No one would have bothered with Raman scattering in optical communication system if it had a very small bandwidth, right, which means this wavelength and only one wavelength will talk to each other. But the gain spectrum of Raman scattering is so large, right, it means that the entire wavelengths within this region will talk to each other with different coupling efficiencies, but nevertheless they all talk to each other, contribute to losses. Okay. So, this is again the harmful effect of Raman scattering, but there are good reasons as to why one can use Raman effect, or good uses of Raman effect as well. One very important effect, or one very important application these days is to implement what is called as phase sensitive amplification. Okay, with only one signal and one Raman pump, one can implement phase conjugation, which in turn leads to phase sensitive amplification, and SRS based phase sensitive amplifiers are being developed, are being actively researched. So, this will put an end to our discussion on nonlinear effects in the fiber. Remember, nonlinear effects are harmful mostly for communication systems, but for all optical signal processing, these are the fundamental good processes that are used. Okay. FWM is a very important useful factor there. Raman effect is very important, Brillouin is important, they are all put to good uses, but in communication systems almost all of them are bad for us. Okay. With this we will stop discussion of nonlinear effects. Thank you very much.